The wood holding up an 800-year-old Norwegian church is stronger today than the wood holding up a house built in 2005, and we cannot build like that anymore even if we wanted to. Not a metaphor, not nostalgia, a structural and material fact that modern engineers have spent decades trying to unpack, and the conclusion they keep arriving at is deeply uncomfortable. We lost something. Not a secret we forgot to write down, not a tool that rusted away. We lost the raw material itself, the trees, and with them, a class of construction that simply cannot be reproduced at scale in the modern world. There are 28 stave churches still standing in Norway. 28. Historians estimate there were once between 1,000 and 2,000 of them. The ones that survived did so without a single steel fastener, without concrete foundations, without pressure-treated lumber or industrial adhesives. Borgund Stave Church has been standing for somewhere between 800 and 900 years. The wood is still doing its job, the joints are still tight, and the black exterior you see in every photograph. Not paint, pine tar, an antimicrobial water-repelling compound the Vikings were producing in industrial quantities from tar pits near Uppsala, Sweden. At least 2,500 years ago, archaeologists have carbon-dated those pits to between 540 and 380 BCE. No folk chemistry here. A systematic large-scale production process for a material that modern wood science has since validated as genuinely effective. The Vikings were running what amounted to a chemical manufacturing operation in the middle of a forest, and the results are still on the walls of Borgund right now. But before any of that, before the tar and the joinery and the churches, we need to talk about the wood itself. Because everything the Vikings built, every ship, every hall, every stave, depended on a material that no longer exists in commercially meaningful quantities. And understanding why it no longer exists is the key to understanding why we cannot simply copy what they did. Old-growth forests produce timber under conditions of intense competition. When trees grow tightly packed for centuries, they fight for light, they grow slowly, and they pack enormous amounts of cellular material into every inch of trunk. The result is tight growth rings, sometimes 10, 15, 20 rings per inch, and a density and resin content that makes the wood almost impervious to rot, insects, and moisture. The stave church pine was not special because the Vikings picked the right species. It was special because those trees had been growing for 200, 300, sometimes 400 years before anyone touched them. When you cut into timber like that, you are not cutting into ordinary wood. You are cutting into something closer to stone. Those forests are gone. What we grow today in managed timber operations is fast-cycle wood. Planted, harvested in 40 to 60 years, light rings, lower resin, higher moisture content, softer cell walls. Perfectly adequate for houses. On the North Atlantic, it would have lasted maybe 50 years. Now here is where the Vikings did something that still impresses materials engineers today, and it starts with a wedge. Every plank on every excavated Viking ship was not sawn, it was split. The technique is called riving, and it works exactly the way it sounds. You drive iron or wooden wedges into a log along its length, splitting it radially, first into halves, then into quarters, then into eighths, producing wedge-shaped planks whose grain runs continuously from one end to the other without interruption. When you saw a plank, the blade cuts across thousands of wood fibers per stroke. Those fibers are severed. The structural continuity of the wood breaks at every cut. When you rive a plank, the split follows the grain. The fibers run the full length of the plank, unbroken. The result is demonstrably stronger, more flexible, and more resistant to moisture penetration along the plank face. There is a modern equivalent. If you have ever bought high-end furniture advertised as quarter-sawn oak, you have bought a product where the manufacturer went to the trouble of cutting boards in a way that mimics radial splitting. Furniture makers charge more for it. The Vikings did it on every single ship plank as standard engineering practice, not as a luxury, as the baseline. And the reason we stopped is straightforward. The industrial sawmill. Sawn cuts are faster. They produce more usable wood per log. They are cheaper. So when the mills arrived, riving disappeared. Not because anyone decided split wood was worse, but because the economics made sawn wood irresistible. The structural trade-off was never really debated. It got absorbed into the cost of doing business at scale. Here is something else about rived planks that tends to get overlooked. When you split wood radially, you expose what are called medullary rays, horizontal bands of cellular tissue that run across the grain, connecting the rings outward from the center of the tree like spokes. When those rays are exposed on the face of a plank, they produce a surface that actively sheds water rather than absorbing it. The grain pattern you see on quarter-sawn oak, that tight, almost reflective fleck, is medullary ray exposure. On a ship hull, that surface characteristic is not decorative, built-in waterproofing at the cellular level. Every Viking ship plank had it, on both faces, as a matter of course. Now take those planks and watch what the Vikings did with them. 5 ships were pulled from the bottom of Roskilde Fjord in Denmark in 1962. They had been deliberately sunk as a blockade sometime around 1070 AD, and the cold, low-oxygen water had preserved them remarkably well. The Skuldelev ships gave researchers the first complete picture of Viking ship construction across multiple vessel types: coastal traders, open-sea longships, ferries. The largest, Skuldelev II, was 98 feet long, a warship, built with overlapping clinker planks, each plank lapping over the one below it, riveted with iron through the overlap, producing a hull that was both strong and, crucially, flexible. Not flexible in a vague, poetic sense, flexible in a documented, measured, engineering sense. The Viking Ship Museum in Roskilde spent years building full-scale replicas of all 5 Skuldelev vessels, completing the set by 2004. One of those replicas, the Sea Stallion, a reconstruction of Skuldelev II, sailed from Roskilde to Dublin and back in 2007 and 2008, nearly 2,000 miles each way, in open North Atlantic water. And during that voyage, researchers measured something that stops engineers cold when they hear it for the first time. The hull twisted 6.2 inches under the stress of open sea conditions, 6 inches of flex across a 98-foot hull. In a single crossing, and it held. The ship did not crack, the rivets did not shear, the planks did not split. For context, a rigid wooden hull experiencing that kind of torsional load would shatter. The structural logic of most boat-building traditions is to resist wave force, to build stiff and strong. The Viking hull was designed to move with wave force, to spread stress across the entire structure, rather than concentrate it at any single point. The overlapping clinker design meant that load passed laterally across every plank seam rather than transferring directly to the frames. The ship writhed like a spine. It absorbed the sea rather than fighting it. In 1893, a replica of the Gokstad ship, built to the same clinker principles, crossed the Atlantic from Bergen, Norway, to Newfoundland in 28 days, averaging 10 to 11 knots. Faster than many sailing vessels built 700 years later. The captain reported the hull flexing visibly in heavy swells and noted that this appeared to be intentional. He was right. It was. There is another dimension to Viking woodworking that modern construction has almost entirely abandoned, and it has to do with timing. Vikings worked wood green, meaning freshly cut, still wet, cells still full of moisture, the opposite of modern practice. Today, lumber is kiln-dried before use. The moisture gets driven out in industrial drying chambers, so the wood reaches a stable equilibrium moisture content before it goes into a structure. No warping, no shrinkage after construction. A post-industrial revolution standard. The Vikings knew wood shrinks as it dries. They built that into the design. A joint cut into green wood and assembled while the material is still wet will tighten as the wood dries around the tenon. The cellular structure locks the joint from the inside. You are not fighting the wood's natural behavior. You are engineering the connection around it. Mortise and tenon joints, wooden pegs, dovetailed corners. All of them get tighter with age in green-built structures. The stave churches were not just built without nails. They were built in a way that made them more structurally sound the older they got. And the corner posts of those churches, the staves, were not set into the ground. Earlier building traditions buried posts directly in soil, which meant ground contact, which meant moisture, which meant rot. The Vikings set their stave posts onto horizontal sleeper beams laid on stone foundations. The wood never touches the earth. Ventilated, exposed to air on all sides, coated in pine tar that repels water and kills microbes. That combination of decisions, foundation design, material selection, surface treatment, is why Borgund is still standing, which makes what happened to the Oseberg ship in the 20th century particularly difficult to look at. Built around 820 AD, buried in 834 AD as a funeral vessel, a burial mound in southeastern Norway containing the ship and the remains of 2 women, along with one of the most extraordinary collections of Viking Age artifacts ever recovered. You cannot build a Viking longship with modern softwood and expect it to flex 6 inches in open ocean and hold together, because modern timber does not carry the cellular toughness that 300-year-old old-growth pine produced under 200 years of forest competition. The wood was the technology, the forests were the manufacturing plant, and we cleared them for farmland, for fuel, for industrial-era lumber demand, faster than they could regenerate. What survives is a set of 28 churches and a handful of excavated ships that keep telling us, quietly and persistently, that a group of people in medieval Scandinavia understood the material properties of wood at a level we are still working to fully articulate. They knew that split wood outperforms sawn wood. They knew that green joinery self-tightens. They knew that slow-grown resinous timber resists everything the North Atlantic can throw at it. They knew that a hull designed to flex will outlast one designed to be rigid. They knew that a post kept off the ground will outlast one buried in it. None of it came from a laboratory. It came from accumulated generations of building things, sailing them, watching what failed, and adjusting. We stopped adjusting when the mills got cheaper. The question that keeps coming back, and it is worth sitting with, is what else we traded away without realizing it, not just in timber, in materials, in construction methods, in the kind of knowledge that only survives when people keep using it. The stave churches are not museum pieces about the past. They are a measurement of distance, a way of seeing exactly how far current practice has drifted from what wood, used correctly, is actually capable of. So here is what I want to know from you. Is there a material or a building method from the past that you think we abandoned too fast? Something we gave up for efficiency that we are quietly paying for now? Drop it in the comments. I read every one, and this is exactly the kind of conversation worth having out loud. If this changed the way you think about the wood in the walls around you, hit that like button and share it with someone who builds things for a living, because this is the kind of video that lands differently when you have held a piece of timber in your hands. And make sure you are subscribed, because next week we are getting into a construction material that modern engineers have been trying to beat for 2,000 years and still cannot.